Now we're recording. At last, 15 minutes in. Final. All right. For those of you who are taking the oral, I will break the class down into sections, so not exactly chapters. The idea is similar to how this was done in like upper classes, where I've given orals like 560, 561. If you want depth, you can choose a section and have your questions on that that are more in depth, or you can choose the breadth option where I can ask from anything but less in depth.
No, we don't want that.
Okay.
I did that last semester. It wasn't a good idea.
Oh, okay.
No, I'm just kidding.
Okay, so there's, well, first I'll identify by chapters. So chapter 1, that is root finding, Newton's methods, fixed point iteration, all that good stuff. Chapters 6 and 11, that is polynomial interpolation, whether it's Lagrange, Hermite, or spline. I mean, that's still interpolation. And then there's chapters 7 and 10, and that is numerical differentiation and mainly integration. Because chapter 10 is all the Gaussian quadrature stuff, so it's lumped into this category. Chapters 8 and 9, and that's polynomial approximation as opposed to interpolation. So in the infinity norm and a 2 norm. And I know nobody likes minimax, but it's in there. Okay, but it makes you feel any better. I don't like it either. In fact, I cut it out of my textbook too. And then finally, chapter 12, that's all the stuff on ODUs. So if you want depth, then you just need to let me know in advance which of those you would like, or whether you want breadth.
Okay, when are we doing this again? The week before finals? The week of finals?
Oh, just whenever.
Okay. Before grades are due.
Yeah, so up through December 15th, the last day of finals.
So, excuse me, 8 and 9 are not the depth. Are not.
These are your depth options.
Okay.
Yeah.
Okay.
Yeah.
So, if we don't want to go through depth options, then how we have to combine two of these?
No, all of them.
The
All of them.
breadth would be, I could ask on anything.
Okay.
Yeah.
The easier questions. So
Yeah, they're
that's
not
Right.
the
as
trade-off.
Yeah. You don't have to know all the nitty-gritty details, just like an overview.
Yeah. Yeah, so you can study everything kind of half-assed.
Or one thing really in depth.
Yeah, or a couple chapters full ass. Okay.
The latter term.
I'm going to use it. I'm going to use it, but I am.
Okay. Yes, we're so innovative here. And now it's immortalized on YouTube too. Okay. All right.
This class is always entertaining.
Yeah, well, good. And then we have, okay, then for the written, of course, the written is comprehensive, since just.
Like, is there like kind of something from like each section or kind of sort of?
Yeah, how do you suggest studying for it? Like, do we need to be prepared to answer questions like that are in the textbook, like we've been doing for
No.
Like, those are like really hard.
Because like, maybe,
Okay.
or is
I don't know how to prepare.
like definitions, I mean like how,
I will send you a old comprehensive.
okay.
Now, I think the only substantive difference between that one and the real one, besides the specifics of the questions, of course, but I would likely make the real one a little bit longer. This old exam had 4 problems on it, but a couple in particular were kind of lengthy to work out. But I'd probably put 5 on. So. Now, those of you who are,
How long do you have to do the written? 2 hours?
that's another thing I want to discuss, because the regular final exam time slot for this class is a Monday of finals week, 4:15 to 6:45. Now, if you really, really don't want to take it during that time, we can figure
Only
some.
one person.
It's
a statement right now.
well, we also don't know about Nikesh and Vivian.
He's doing oral.
Okay,
I'm assuming Vivian's doing it.
so you're the only one?
I think so.
Okay. Could you take it at that time?
Yeah, that's fine.
Okay.
It might be a little closer to 4:30 when I get here,
Okay.
just depending on
All right.
what's
Well,
traffic.
I'll stick around.
Yeah.
So,
But, I mean,
yeah. Well, yeah, I mean, because you would have 2.5 hours for it, but
right.
yeah. Generally, comprehensive exams of either kind, master's or PhD, are supposed to be 2 hours. But if I'm proctoring it, I'm going to give 2.5. So, don't tell anybody.
Are people really that strict on time?
Not that I know of. I've had cases where if someone taken a comprehensive exam, I put away to I put them in a room and I forget about them. But so
I got extra time and didn't know good.
and you took a comp.
No, not yet. I'm just talking about a regular test for him. I haven't even got that far yet.
Oh, okay. Are you taking a class of them now, or like a topics thing, or? Oh, I'm so sorry.
Program bases, model modules,
Okay. So
syzygy, I don't even know what all.
I haven't even heard of that stuff. So, okay. Okay. Now, those of you who are planning to take it for PhD comp, now the way it's supposed to work is, per Dr. Schroeder, to have the exams written and graded by teams of 2. Due to things coming up like certain faculty not bothering to answer emails or anything like that, I think this can be enforced a little more loosely than it has in the past. Well, because in this case, for 772, I would even want to write the test, and then I would have to enlist another faculty member to take a look at it and make sure it's not too easy in their opinion or something like that. And then I guess I would be the primary one to grade it, and then that a second person, maybe Dr. Schroeder or Dr. Ding. In fact, for 772, it would certainly be one of those 2.
Dr. Schroeder?
Well, he has looked at comps for 771, even though that's not in his area either. But yeah, but probably Dr. Ding.
What about Dr. Zhu?
Well, possibly, yeah.
Okay.
Dr. Zhu has never taught 772.
Oh, so it's kind of more...
Only Dr. Ding and I have done it.
Okay.
Yes, so just make sure it wasn't too generous with partial credit or something like that, or that sort of thing. Yeah, so it's kind of screwy, but
I think this makes sense.
yeah. So, yeah. Well, it's a good check to make sure someone doesn't write an exam, but it's too too long or anything.
It's not biased, I guess.
What?
And it's not biased.
Yeah.
Like when you teach it and you make sure everyone passes and you're like, oh, it's because I'm a great teacher. But it might be, not like you specifically. But,
Yeah.
But it's really, it's
Make
because
sure
of
that
Yeah.
confidence too easy. That makes sense.
Okay. So you think you'd both would take it next semester or sometime, or?
Yeah, I was thinking like early next semester
Okay. Yeah. Fine with me.
when I don't have like anything else to think about.
Okay.
Is there anything like a study guide or comprehensive?
I've sent really informal study guides by email in the past. But yeah, I'll. What do you think you'd want to do it too, or later, or I don't know.
I don't know. I don't think about it.
Okay. Well. When it comes time for me to send them a study guide, we'll talk. Okay. All right. Let's cover stuff. Alright. So I was in the middle of covering stiffness before. And I talked about one-step methods. So now for multi-step methods. For a general multi-step method, we have this form with your alphas and betas. Okay, and we apply this to the test equation, which is y prime is equal to lambda y, and we make sure that, or we assume that the real part of lambda is 0. That's to ensure as t goes to infinity, the y of t goes to 0, that we have exponential decay, not growth for a stationary solution. All right, so if I plug in here f of ty is just equal to lambda y, then what I get is this equation satisfied by the y values, alpha I minus h lambda yn plus 1. Oh, wait, I forgot the betas. H lambda beta I. So now my solution values satisfy this recurrence relation, where the coefficients of a recurrence relation depend on h and lambda. Now, we've dealt with recurrence relations before when talking about stability in the root condition, where we had a different recurrence relation, and we said, well, then y is the solution of this recurrence relation has this form. Yn is like some constant n raised to some integer power times a root lambda I. Oh, I don't want to use lambda in this case because I'm using lambda elsewhere. Mu I to the nth power. So the solution has this form. Now, when we saw this form of recurrence relation before, these values were the roots of a polynomial, and that led to the root condition. These are also roots of a polynomial, but a different polynomial. So the mu's are the roots of what is called the stability polynomial. And that polynomial is, it's a function of mu, but it has h lambda as a parameter because h lambda is involved in the coefficients. So we have alpha naught minus h lambda beta naught times mu to the s. So it's a polynomial degree s. Then alpha 1 minus h lambda beta 1 mu to the s minus 1. And we keep going down to the lowest degree terms. In mu plus alpha s minus h lambda beta s, and that's the constant term. Okay, so we formed this polynomial from the alphas and betas of a multi-step method, and then h lambda is involved in the coefficients for whatever h lambda we've chosen. And then we get our polynomial degree s, we get its roots. And these coefficients, as before, these range from 0 to the multiplicity of mu I as a root minus 1. So if all the roots are distinct, then all the PIs are going to be 0. Okay. So our solution, yn, is required to decay to 0 as n goes to infinity. So in order to make sure that happens, to achieve exponential decay, we have to require this condition that the absolute value of all of these roots has to be strictly less than 1. So the roots of the stability polynomial must be less than 1 in magnitude. So this is a little different from the root condition. In the root condition, we wanted solutions that either decay to 0 or they remain stationary or remain constant. In that case, we allowed a root to be equal to 1 in absolute value, as long as it was a simple root. But now we don't even want that. We insist on exponential decay because we're assuming that lambda has a negative real part. So it's a somewhat different stability condition. Okay. So let's look at an example of a multi-step method, and we try to get a hold of the roots of a stability polynomial. Unfortunately, it's generally not easy to do. Okay, so we have a 3-step Adams-Bashforth method. Okay, so we have yn plus 1 is equal to yn plus h over 12, 23 fn minus 16 fn minus 1 plus 5 fn minus 2. All right, so if we look at our coefficients, alpha 0 is 1, alpha 1 is minus 1, alpha 2 is 0, and alpha 3 is 0, which is typical of an Adams method. And then beta naught is 0 because this is an Adams-Bashforth method. It is explicit. Beta 1 is equal to 23 over 12. Beta 2 is minus 16 over 12, so minus 4/3. And beta 3 is 5/12. Okay, so those are all of our coefficients of our method. So the stability polynomial this is why I wrote out all the coefficients. They're always equal to alphas minus h lambda times the corresponding beta. So we have q of mu and h lambda is equal to 1 minus 0 h lambda, so just 1 times mu cubed, so that's the leading term, plus minus 1 minus h lambda times 23 over 12 mu squared plus 0 minus 4/3 h lambda mu, and then plus 0 minus 5/12 h lambda. Okay, so this is our stability polynomial. Now, for all but the simplest multi-step methods, generally we cannot get a formula for the roots of a stability polynomial. All we can do is choose the specific values of h and lambda, or at least the product h lambda, and then get the roots. And see if they have absolute value less than 1 or not. So I'll let lambda equal minus 100. And I'll choose h to be 0.1. So that means that h lambda is equal to minus 10. So now I can fill in h lambda equal to minus 10 and figure out the roots. So in that case, we get a root that's equal to minus 18.884, which is much greater than 1 in absolute value. So we would get an exponentially growing solution in that case. On the other hand, if I choose h equal 0.005, so h lambda is equal to minus a half. So then the largest root in absolute value is 0.924. So all the roots are within the unit disk. So in that case, your solution will go to 0 as n goes to infinity. So we have the exponential decay that we're supposed to get. Because in this case, lambda equals minus 100, we're supposed to get very rapid exponential decay. But if you choose h to be too large, that's not going to happen. Now, one thing that's worth pointing out is, as h goes to 0, what ends up happening is this stability polynomial ends up being depending only on the alphas. And in that case, you're looking at the polynomial that's used for the root condition. And for Adams methods, for instance, they have 1 equal to a root that's on a unit circle, and then 0 is a multiple root after that. So that's the connection between this kind of stability and then the 0 stability that I mentioned earlier. Okay. Generally, implicit methods, you can get away with larger values of h than for explicit methods. Okay. All right, so that's for a multi-step method. And I want to recall briefly what we did to ensure exponential decay for a one-step method. Okay. So for one-step method of this form, yn plus 1 is equal to yn plus h phi of tn yn h. You'd apply the test equation, you'd apply this one-step method to the test equation, and what you would get is, okay. You get something of this form, yn plus 1 is equal to q of h lambda times yn. And we require, for exponential decay, that this function q of h lambda in absolute value be less than 1. So that's the stability criteria, absolute stability criteria for one-step methods. So to contrast and sum up, the region of absolute stability is equal to the set of all values of h lambda in the complex plane. So you can think of h lambda again as a single entity, a single number, such that absolute value of q of h lambda is less than 1 for a one-step method, or the absolute value of mu I is less than 1 for a multi-step method where mu sub I is a root of the stability polynomial. So for whatever method you have, one step or multi-step, this is how you check whether H lambda is in a region of absolute stability. And the way we interpret the region of absolute stability in either case is then whatever method you have, your one-step or your multi-step method, it produces a solution of y prime equals lambda y, such that yn is guaranteed to go to 0 as n goes to infinity. That you're going to get exponential decay as required, since we're always assuming that lambda has a negative real part. Okay. All right, so in other words, you're guaranteed to get the correct qualitative behavior. Okay. All right. So, now the thing is, a one-step or multi-step method for that can always be that's generally well behaved. Like it's consistent. You can show in the case of like zero stability, it's zero stable and therefore it converges. This is not really about that. This is not about convergence because so zero stability for multi-step methods or for one-step methods, the condition that we had was Lipschitz continuity of your function phi that defined your one-step methods. Those concepts are about convergence. As h goes to 0. So as h goes all the way to 0, do we get the exact solution of the ODE? On the other hand, so by contrast, absolute stability is for choosing a specific positive h. So you produce a numerical solution. You are not letting h go to 0. So this is about the real world here. We don't get to take infinitely many time steps. We don't get to have an infinitely small h. Do we get the behavior we're supposed to get? It's supposed to give some guidance on choosing h so that you will get the correct behavior. Now, since h lambda are kind of taken together, if lambda should increase, like the size of your f, that means that h should be made commensurately smaller. So what kind of size of h lambda is needed to make sure that your solution is reasonable? Okay. So So we're really talking about two different things. It's very unfortunate that people who developed all these things decided to refer to both of these concepts as stability, but we're stuck with that. Okay, but here's my attempt to distinguish the two. Now, the goal in designing a method is we like to have a larger region of absolute stability. And the reason for that is if you have for a given, like a fixed lambda, if you have a nice large region of absolute stability, you can get away with using a larger value of h. Therefore, you can take fewer time steps. Therefore, your method is more efficient. Because now of course, the larger you choose h, the less accuracy you have. But if you're just trying to get something in the ballpark, something that behaves reasonably, then this is a good thing. Okay. Now, the ideal situation is that the method is A-stable. And what is meant by A-stable is that the region of absolute stability contains the entire left half plane. In other words, the set of all complex numbers with a negative real part. So in other words, you can choose h to be infinitely large, arbitrarily large, as large as you want, and still get exponential decay for whatever value of lambda that you have. Okay. So that's like the holy grail of for absolute stability, is to have methods that are astable. The problem is, it almost never happens. Now, I could show you two well-known methods that I brought up before, that are astable. But the unfortunate thing is, you can't get astable and high-order accuracy. So the two methods I could show you that are astable are low-order accurate methods.
Wait, why can't you?
Ask dahlquist.
Okay.
I'll show you his theorems in a bit. Okay. All right. So simplest example is Backer-Euler is astable. Okay. So that is y plus 1 is yn plus hf of tn plus 1 yn plus 1. So now, if I have y prime is lambda y, I have yn plus 1 is equal to yn plus h lambda yn plus 1. So now I can solve for yn plus 1. And let's quickly do the algebra here, because you all are such math whizzes. What I get is 1 over 1 minus h lambda yn. And this is my function q of h lambda. And I need this to have absolute value less than 1. So if we keep in mind that lambda has a negative real part, then why is it that I can be assured that that really is the case? So Um, okay. And if you want, you can assume that lambda is real, just to simplify things. But the point is, lambda has a negative real part. So what do we have for a denominator relative to the numerator?
Absolute value.
Um,
Course here.
Oh, yeah, but the thing is, if we're going to have this whole fraction be less than 1 in absolute value, then what do we need to happen here, algebraically?
Okay, wait, hold on. I was definitely looking at that wrong. You were saying that. Okay, so for that to be less than 1 and Q, whatever that says.
Okay, Q of H lambda is just
that-
this fraction.
Okay, it's just that fraction.
Yeah.
So if it's less than 1, then the denominator has to be greater.
Yeah, so I want 1 minus H lambda, and that's got to be greater than 1. But lambda is as negative real part.
But that's fine though, because then it's 1 plus.
Bingo! That's exactly why this works. So, yeah. So if I let H lambda, it's a complex number, but I call it like U plus IV, and U is negative. So what we get is, the absolute value of a complex number is square root of real part squared plus imaginary part squared. So it turns out, no matter what V is, this whole thing is going to be greater than 1. So so everything works out. So, so this is always true. Okay, so that's a first order accurate method that is astable. Now, there's only one astable multi-step method, and that is the trapezoidal method, which also could technically be characterized as a Runge-Kutta method too. Well, yeah, it can be, but okay. Let's specify it as a multi-step method. So yn plus 1 is equal to yn plus h over 2 fn plus 1 plus fn. So this is also an implicit method. So then, if I form my stability polynomial, alright, so we have alpha 0 is 1, alpha 1 is minus 1, beta 0, okay, so beta 0 is equal to 1/2, and beta 1 is also equal to 1/2. So actually, this is a one-step, multi-step method. So the stability polynomial is alpha 0 minus h lambda beta naught times mu. And the constant term is minus 1 minus h lambda over 2. So that's our stability polynomial. This is a one-step method, so it's degree 1. So there's only one root. So the root is 1 plus h lambda over 2 over 1 minus h lambda over 2. So how can we be sure that this is going to be less than 1 in absolute value? Again, h lambda is negative real part. it's the same thing. That minus a minus makes a plus. Yeah, so it's not very interesting algebraically after the last example, but yeah. So this is also less than 1 for real part of lambda being negative. All right, so those are two astable methods. Okay. Now, why don't I have this here? It doesn't make any sense. Okay. All right, now, so for higher order methods, you don't have that large a region of absolute stability. But generally, implicit methods tend to have a larger region of absolute stability than explicit ones. So that's one reason why people like implicit methods. Okay. Now, I think I'm up to, yes, the last piece of essential material. And I mean, a drawback, of course, of implicit methods is you have to use some root-finding method. Like Newton's method at every single time step to advance your method forward. But if you can get away with larger time steps, then that can offset the expense of that root-finding method. Well, actually, all right, I'm doing pretty good on time, so I'll, even though there's a rather odd place in the notes to put it, I'll go ahead and lay it out. All right. So, so as I mentioned, implicit methods large regions of absolute stability. So the pro to this is you can use larger h. The con is you need an equation solver or root finding method. So the idea is yn plus 1 is a root of this equation. Big F of y is equal to 0. And I could define f of y. It basically comes from your multi-step method. That's alpha 0 y, which this is your n plus yn plus 1, plus the rest of your alpha terms. Because keep in mind, all of your other y's, yn, yn minus 1, yn minus 2, those are all constant, treated as constant at this point. Minus h beta naught f of tn plus 1 y, so you plug in your y value you're trying to compute into your f, and then minus h some, to have all your other f terms. Oh, that should be n plus 1 minus I. Okay. All right, so this is your function you're trying to find a root of. Now, how complicated this is just depends on really the complexity of little f, your time derivative. So, for example, if you do your Newton iteration, then your latest value of yn plus 1 is your previous value of yn plus 1. And then you're plugging that into f, and you also have f prime. And the thing is, what is f prime? You're just going to take the derivative of this, which is not much to it. It's just going to be alpha naught minus h beta naught df dy tn plus 1 and y. Okay, so that you'll use down here. Okay, so as long as you have the partial derivative of f with respect to y available, then Newton's method is no problem. If you'd rather not, if it's not convenient, then you can use like a secant method instead. As far as the initial guess goes, you could use like yn as your initial guess, or you can maybe compute a different approximation of yn plus 1, like using a one-step method, or an Adams-Bashforth method, something like that. Okay. Now, the last piece of essential material of the whole semester. Dahlquist theorems. Okay. Actually, I'm going to look him up really quick. Actually, I have an old numerical analysis text that was co-written by dahlquist. Oh, yeah, he passed away not too long ago, in 2005. Oh, of course, Uppsala, Sweden. Uppsala University in Sweden is like a hotbed of numerical analysis worldwide. Like, it's amazing what they do there. I've been there. I know some of the people there. In fact, one of them I learned all about eigenvalues from. Well, my first advisor, Joe Oliger, he got his degree there. Well, Brianna, for Brown book that you have, yeah, it came out of there. Those are all Uppsala people one way or another. Okay. Let's see. All right. Oh, so now SIAM has a dahlquist prize awarded to a young scientist, normally under age 45, for original contributions to fields associated with him, especially numerical solutions of differential equations and numerical methods for scientific computing. That's pretty broad, but so okay, something for y'all to go for. Okay, I'm out of time. Okay. Now, the thing is, these theorems are kind of letdowns, and that are kind of negative results. Well, the first one's not. There's I've kind of given this theorem already, but it's nice to have it formally stated. So the first one is dahlquist's equivalence theorem. So the equivalence theorem says a consistent multi-step method with its local truncation error and yes, it's probably the sloppiest statement of dahlquist theorems ever, but I'm tired. So if its local error is pth order accurate, it is convergent with global error order h to the p. If and only if it is zero stable. So that's a previous sense of stability that I defined some time ago about the root condition. That the roots being either within a unit circle or on a unit circle if it's a simple root. Now remember, local truncation error is the error committed during a single time step. Global error is the accumulation of errors over all the time steps. So they have the same order, but converges. So normally I say, consistency plus stability implies convergence, and that is part of this theorem, but now we have this if and only if aspect to it. Okay. So this ties together the important concepts we've been discussing with regard to time-stepping methods about consistency and stability, convergence, and how they all relate to each other. Okay, now here are theorems that are the letdowns. So we have dahlquist's first barrier theorem. Okay. So the first barrier theorem says it imposes a limit on the order of accuracy of a multi-step method. So the order of accuracy of an S-step method is less than or equal to, I should mention also a zero stable S-step method, is at most S plus 1 if S is odd, and S plus 2 if S is even. Well, one example that I gave, Simpson's method. It is a two-step method that is fourth order accurate, and it is weakly zero stable. So it hits this bound. Adams-Moulton methods, so those are implicit. They have an order of, they're all strongly zero stable. They have an order of accuracy as equal to S plus 1. So if S is even, they could hit S plus 2, but Adams methods don't. They're always S plus 1. Okay. All right. But so the thing is, it may be possible to get an S-step method that has an even higher order of accuracy that violates this, but then it's not zero stable. And therefore it's not going to be convergent either, so why bother? Okay. And then finally we have a second barrier theorem. That is about the region of absolute stability. So there's a few items here. First of all, there's no explicit astable method. If you have an astable method, it has to be implicit, like the examples I showed you. Okay. Second item, that if a method is astable, that means that the order of accuracy is at most 2. Now, as an example, we have the the trapezoidal method. That's second order accurate, and it has a only one root of its stability polynomial because the stability polynomial is linear. So I would imagine that I've not seen the proof of a second barrier theorem as to why it's impossible to have a higher order accurate method be astable, but it probably has something to do with what you can say about the roots of a stability polynomial. If you have such a low degree of your stability polynomial, at least a low order of accuracy, then you're probably able to prove something more about the roots. But once you get the higher accurate, you have more roots, you can't really control their magnitude. And the last statement is the astable method. So out of all astable methods that exist, so the most accurate of all second order astable methods. So not only is the order of accuracy the best that you can hope for, too, but by most accurate, what I mean is the constant in front of the error, the constant in your error formula is as small as possible. Is the method I wrote down over there, the trapezoidal method. Okay. So the best astable method is already known. So if anyone has some goals of coming up with a better astable method, forget about it. Okay. Now, one thing, what people have tried to do instead, now that they have this barrier when it comes to astable methods, is they try to develop methods that their region of absolute stability might not contain the entire left half plane, but maybe it could contain certain key portions of it. Like there are higher order methods that contain the entire negative real axis. So for real lambda, you have a limited sense of astability there. And that could be important, for instance, within systems of ODEs where there's this one term, like a diffusion term, that is dominant, and then you have these lower order coefficients, so your kind of problems. Depending on the coefficients involved, where it may be possible to design an astable method to accommodate something like that. Because a PDE like that, if it has only diffusion and then you have reaction terms, there's no advection term that would introduce a complex part, then these kind of methods would work very well for it. Although it's never use KSS. So now, it might seem at first glance, if anyone's looked at any of my papers on KSS and what I said about stability, that what I have there contradicts this, because KSS methods are explicit and certain ones are unconditionally stable, which is similar to astability. But the fact that, the thing is, KSS methods do not fall into this category of a multi-step method. They're component-wise methods.
They're also stable.
Yes. Yeah, and scalable and all that other good stuff. So the thing is, if you're not satisfied with what's possible with certain types of methods, you just do what I did, invent a whole other class of method, and then the rules are changed. So, yeah, it seems to have worked pretty well. Okay, now the funny thing is, as we get, okay, we're almost out of time. Okay. Getting more comments on my post. It's so funny. Okay, yeah.
I know, they're popping up now that I commented.
Yeah.
Wait, what'd you
You gotta go look. It was hysterical. I was like, he can't be serious.
Okay. Now, I actually do have more notes, but I'm debating whether I should bother doing it, or I'm not going to today because we're almost out of time. But so I have a section at the end of the notes, analysis of multi-step methods, and all I do in this section is I look at certain multi-step methods and do the same kind of stability analysis. Like, what is the stability polynomial? What is the order of accuracy? All that stuff. The only reason I even wrote these notes way back the first time I taught the class was when I was covering all this stuff, I screwed it up so badly, and I felt so bad about it that I just basically gave myself a do-over of a lecture and wrote this last section. Now, if you guys really, really want me to on Wednesday, I can cover it. Well, I don't think it would take the whole class time. However, regardless, I would recommend looking at it, where I guess, here's a specific multi-step method. You figure out the order of accuracy. You figure out, is it zero stable? What can be said about the stability polynomial? And can you conclude convergent? Things like that, because these are excellent material for comprehensive exam questions. Well, okay, written comprehensive exam questions. Or at least like carrying out the specific manipulations. So I guess the subject of these theorems might be excellent oral exam questions. What does the second dahlquist barrier theorem say? Stuff like that. But I'll have more to say about either kind of final on Wednesday. If someone wants to know about multi-step methods, maybe I can cover some stuff. But yeah, the essential stuff has been covered, so yay. Alrighty.